Good morning. There is one last item on lesson 3.4 on solving on the application of determinants, where we can use determinants to solve a linear system that has a unique solution with n equations and n unknowns. This is basically a method which gives you the solution in terms of determinants, so that's why it's an application of determinants. I should say that actually in practice you seldom use it for the purpose of solving systems, because especially if the system is, in general it's just easier to use elimination or Gaussian elimination using the row echelon form to solve the system itself. But its value of getting the solution in terms of determinants is because, well, first of all, you can use technology to set up easily the formula for the solution, as long as you have a command, for example, that you can call on a computer to compute the determinant. And another thing that you may notice, for those of you who take differential equations, there are some formulas for solutions of certain differential equations that are given in terms of basically solutions of systems, and then those will be provided in the form of determinants using this Cramer's rule, because basically this allows you to have a nice compact format of that solution. So let's actually write down the main idea behind the rule. So let's just write in words what I just mentioned briefly. So suppose a n by n system, linear system of equations, which, remember, in the generic form is given like this: a matrix A with n rows and n columns times x equals b. So suppose this system has a unique solution, and remember we learned on this lesson that this is equivalent to saying that the determinant of A is not equal to 0. Then we can compute the solution of it using the Cramer's rule, which provides the solution in terms of determinants. That doesn't say much, obviously, but let's illustrate what that method entails. So suppose x1, x2, xn are the variables, right? The unknowns of the system. And then we have a couple of notations. Denote by delta the determinant of A, right? So the determinant of A, the matrix of the system. And again, notice that delta is not going to be equal to 0, right? So this method only works for systems in which you have a unique solution. And pay attention here, denote also by delta xi the determinant obtained from A by replacing the ith column of A, right? So the ith column of A with B bar, right, which is the right hand side. Of the system itself. Then the solution of the system is given by x1 equals delta x1 over delta x2 delta x2 over delta dot 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 xn equals delta xn over delta. Okay, so that's the Cramer's rule. Each solution is obtained by the ratio of two determinants. The one on the top is the determinant of the matrix by replacing the ith column with the right hand side column, and on the bottom is the determinant of A, which notice you can divide by it because it'll be not equal to 0, right, if the system has a unique solution. So let's illustrate this with two examples, because this is one of those problems in which looking at the example makes it much clearer. So I'm going to actually start with a 2x2 example, because I think that's probably the easiest one to illustrate. But again, I'll do also a 2x2 just to have like a non-trivial one, because remember, in the 2x2 case, you rarely do this problem by hand. I mean by the Cramer's rule, right? All right, so let's look at the first example, and let's make a system that has a nice solution. So suppose you have x1 minus x2 equals sorry, the software cut me off for and I had to restart this this slide. So let's continue with the first example. X1 minus x2 equals 3, and that's the first example, right? 2x1 plus 3x2 equals 1. So again, let me write down again the formula. So x1 will be delta x1 over delta, x2 will be delta x2 over delta, and then xn delta xn over delta, which, right, the top is the determinant of the system with the ith column replaced by the right hand side. So let's see how that plays out in this particular system, right? So delta will be the matrix of the system itself, so 1 minus 1, 2 and 3. So that's 1 times 3 minus 2 times negative 1, which is negative 2. That's 5. And then delta x1, pay attention here, we're going to replace the column 1, 2 with the right hand side, 3, 1. The other one stays the same. So this determinant is 9 minus negative 1, which is 10. And then finally delta x2, we're going to replace column negative 1, 3 with the right hand side, 3, 1. And this will be 1 minus 6, which is negative 5. So according to the Cramer's rule, then x1 will be delta x1, which is 10, over delta 5. That gives me 2. And then x2, delta x2, which is negative 5, over delta, which is 5, and that's negative 1. So you can see in the 2x2 case, actually it's a wash. It's pretty fast because determinants are fast to compute. In the 2x2 case, so you can use the Cramer's rule again if you have a unique solution. For larger systems, as you'll see in the second example, so this is example 1, let's do another one with a larger matrix. It takes longer, although it depends on how fast you can compute those determinants. So let's do this example. The first equation is x1 minus x2 plus x3 equals negative 2. Then x1 plus x2 equals 3. And then x2 plus x3 equals 1. So notice we have 4 determinants, of 4 there are 3 to compute, right? Because we have 3 roots in total. All right, so let's start with delta, which is 1, negative 1, 1, 1, 1, 0, 0, 1, 1. Let's make some zeros, extra zeros. We're going to do row 2 minus row 1. So we're going to subtract row 1 from row 2. 1 minus 1, 1 minus negative 1, and negative 1. Expand by the first column. It's 1 to the power 1, because it's negative 1 plus to the 1 plus 1. And that's 2 minus negative 1, which is 3. So delta is 3. Alright, moving on with delta x1. We're going to replace 1, 1, 0 with negative 2, 3, and 1. Right, so you pay attention to the first determinant here, right? And then copy the other columns. Negative 1, 1, 1, 0, 1. Alright, so let's subtract row 3 from row 1. Yeah, so row 3, or row 1 minus row 3. Update, sorry, my tablet. Alright, so then we're going to have minus 2 minus 1, that's negative 3. Notice you have many ways to do the zeros. This is just to make a 0 on the top here. The idea is to make zeros, as many zeros as you can on a single column, so you can have only one step in the cofactor expansion. So minus 2 minus 1, minus 1 minus 1, negative 2, and 1 minus 1, 0. Copy the rest and expand by the last column. Right? So we're going to have, again, just remember 1, negative 1 to the 3 plus 1, row 3 plus 3, right? Row 3, column 3, which is plus 1. And you're left with a minor negative 3, negative 2, and 3, 1. And that's minus 3 minus negative 6. That is 3. Delta x2. First column in the original matrix stays the same, 1, 1, 0. Now the second column becomes the right hand side, minus 2, 3, 1, 1, 0, 1. We're going to do the same, row 3 minus row 1, or row 1 minus row 3. 1 minus 0, negative 2, negative 1, 1 minus 1. Make sure you pause and slow down if you want to catch up with the computation. Normally, if you do these zeros, I mean, if you make these row operations enough, if you practice enough, you could go, you know, relatively quickly, especially if you have easy numbers in the matrix itself. So this leads to the minor 1 minus 3, 1, 3. 3 minus negative 3. Of course, I made it so that the numbers are nice to illustrate the method. So delta x3 going all the way back again to the original matrix. First columns now are the same. And we replace the last column with minus 2, 3, and 1. So we take advantage again of the existing 0, and let's make a 0 another one. We're gonna make it on the top, so we're gonna subtract row 2 now from row 1. 1 minus 1, 0, negative 1, negative 1, minus 2, minus 3, negative 5, 1, 1, 3, 0, 1, 1. Let's pay attention to the sign component of the cofactor expansion, right? Because we're going to have 1, and the signature component is minus 1 to the column or row 2 plus column 1. So there's a negative from the cofactor expansion. And the minus that is left is negative 2, negative 5, and 1, 1. So it's minus, and now the determinant, negative 2 minus negative 5, which is plus 5 actually. So what does that give me? 5 minus 2 with a minus, that's negative 3. Finally, the solution of the system. Delta x1 over delta, that's 3 over 3, which is 1. Delta x2 over delta, 6 over 3, which is 2, and then delta x3 over delta negative 3 over 3, that's negative 1. All right, so that's the Cramer's rule. I think, let me see if I remember correctly, there is a method of finding, because many of you who watch this lecture, I mean, my students, I mean, not the audience, the global audience, but you, my students that are watching this, most of you will take in parallel the class of differential equations. So if there is time, usually instructors might cover this topic of finding a particular solution of systems of equations via, not systems, let me think. Yeah, the method of variation of parameters for non-homogeneous higher order equations, like second order equations. So in that case, yeah, in that case, there is a method which involves actually solving a 2x2 systems, which leads to the formula written nicely in form of a solution of a system via the Cramer's rule. So you may see this as part of the formulas involved in that equation, in that solving for that equation. So that's it for this lesson. I'll see you next time.